Okay, so this problem asks us to give a combinatorial proof that this left-hand expression is equal to this right-hand expression. So before we dive in, I think it's important to just refresh on some basic terminology. So first, a combination is an unordered selection of k elements from an n-element set. Basically, it's just like a size k subset. The binomial coefficient n choose k is the number of such k combinations. A good way to think about this is the number of ways to choose k elements from n elements. So let's say we have like a 4-element set and we want to do 4 choose 2. We're basically finding the total number of ways to choose 2 of those elements. So we could choose a triangle and a circle, we could choose a circle and a square, and so on. And going over all those possible choices gives us 6 possible combinations. So that's why 4 choose 2, for example, is 6. Now for the combinatorial proof, our goal is to show that the left-hand side and the right-hand side count the same set. And we do that by going through step-by-step process combinatorically on how we achieve the cardinality of the set that we come up with. So for the problem, they give us a useful hint, and usually you won't see hints on these kinds of problems, but I think this one's good because it shows you how to kind of approach them, how to think about them. So our hint is to think about different ways to select a team with one member designated as its captain. And so this kind of allows us to define our set S, which is the set that will be showing that we can count over with both sides. So we define the set S as the set of all ways to form a k-person team from an n-person pool and choose one team member as captain. Okay, so we're choosing teams, and for each team, we're choosing captains. So getting started on the left-hand side, we know from before that n choose k is the total number of ways to choose k elements, right? So we can kind of think about that as choosing teams of size k. So if we have n players to choose from and we want to form k-person teams, then the total number of ways to do that would be n choose k, right? So then we can define n choose k as the number of possible team combinations, okay? And then for each team, we need a captain, right? And since the captain comes from the members, that means that there are k choices for the captain. So for each team, we have k choices for captain. And by multiplication rule, that gives us k times n choose k, right? Equals the number of possible teams with captains. And, this is basically this is exactly what we're counting for S. And so to put this in a more concise way, we first choose the k-member team. And of course, we make sure to cite the binomial coefficient. So by the definition of the binomial coefficient, there are n choose k ways to do this, since there are n choose k ways to choose k members from n players. And for each team, we have k choices for a captain. So the total number of ways to choose a team and a captain is k times n choose k. And of course, we also cite the multiplication rule, right? And, this is equivalent to the left-hand side, and this demonstrates that we count over S, right? Right here. Thus, the left-hand side counts S. Okay? Now let's think about the right-hand side. So for the right-hand side, we can think about this as starting with the captain first. So for captains, we have n choices for a captain, right? Since there are n players to choose from. So if we count the captains first, that means that there's n choices. Now, once we choose a captain, that means that we have to choose the remaining teammates, right? And since we have k-person teams and we've already locked in one choice for one of the team members, that means that we have to choose k-1 remaining teammates. And we choose that from an n-1 player pool, since we already locked in our choice for a captain, right? So then for each n choice of a captain, we do n-1 times k-1 potential choices for team, again, by multiplication rule, okay? So to put this in a more concise way, we first choose a captain, and there are n choices for captain, and then for each captain, we choose the remaining k-1 teammates from the remaining n-1 players. And again, by the multiplication rule, we get n times n-1 choose k-1. And we should also make sure to cite the binomial coefficient here too. But yeah, and then of course we include that, each side counts S, And this is the essence of the combinatorial proof. We show that both sides count over the elements of S, thus showing that they're equal. Thank you.